Hi everyone, thanks for carving out some time to spend with me here on my channel. Today I'm going to be talking about image processing in PixInsight with comet data. There's a bright comet in the sky right now. Now it used to be that comets would instill dread and fear in the hearts of men and women everywhere. But now, today, pure delight when we are so lucky and fortunate to see a nice comet in the sky. The comet that's in the sky right now is Comet Leonard. And it may become visible eventually, perhaps when the moon gets out of the way, by your unaided eye as it comes around the sun. I think, though, it's a really good photogenic comet because even with a small telescope or a digital camera and perhaps a nice lens, you can take a picture of it, and that's exactly what I did. But what really makes this a special comet for me, it's with delight that I was asked by the discoverer himself to take a picture of it. Greg Leonard works at Mount Lemmon for the Catalina Sky Survey. He works at the same mountain that I work at for Stewart Observatory and the University of Arizona. And many months ago, after discovering his comet, he's found many others. Not all of them become bright as they orbit the sun, but this one has lived up to its destiny. And he asked me, would I take a picture of it when it comes around? I said, of course, sure, that would be very exciting. And I did just that. So you're going to see some of that data in this particular video. Now, what I'd like to demonstrate is my approach to processing cometary data in PixInsight. And I'm going to be doing it differently. Right now, if you watch online and you'll see people, YouTubers and things, explaining, because the comet's in the sky, how do you stack images and produce a nice comet picture? But there is kind of a standard method that is usually explained. I'm not going to do that. I'm going to do something different. It's something that I think is an improvement upon the standard method, and I hope you enjoy it. Of course, it comes with some risk, right? Because it's new. There isn't another example out there. So I'll be showing you something that I hope it has a lot of takeaway from it. I show it in detail, of course, in my videos at Atom Block Studios. So I am hoping that this will want to make you become a member. There's still plenty to take away from this very high level description of what I did to process the comet image, in this case, Comet Leonard. So the last bright comet that was available was one of the first of the few that I had a chance to process in PixInsight, and that actually was Comet Neowise from a little more than a year ago now. But Comet Leonard is a really nice one. It doesn't have, it's a fairly simple comet, if you will. It doesn't have all these streamers and things going on. So it's a good way to demonstrate in general how to process comet imagery. I hope you enjoy this lesson. Again, thanks for spending some time with me, and let's just get right to it. So I'm going to begin by showing you the results first. Here is what the comet looked like on the morning of December 3rd when it was passing in front of the beautiful globular cluster M3. This particular image is the first one that I had an opportunity to work on. I haven't worked with comet data in a long time, and it is the first one that I've used this technique, and I think I did okay. One of the cool things about the comet is that this field of view is 4 degrees across, roughly, so the comet's tail stretches more than 4 degrees across the sky. It's actually quite large. So that I thought was really interesting to be able to capture. Now, the data that I actually am going to be showing you right now is this taken from the 6th, where there isn't a background beautiful star cluster, but the comet's still nice against this beautiful star field. So this is a very typical kind of example of what working with cometary data would be like. And I have a cheat sheet that I put together. Now, I don't have nice screenshots because I made a video. This is all based on a video that members of Atom Block Studios get to watch in detail and see what I did. But I'm highlighting some of these steps here, and I'll show you some of the important parts of it in PixInsight. So the first thing about the data is that there's only so much time where the comet in the morning is getting above the observatory wall and before it's twilight. So there were about 75 minutes, 80 minutes worth of time. I took 5 times 5-minute exposures in each of red, green, and blue filters. So this is a mono camera, and I cycled between the filters in order to capture the data. So I'm going to, or what I did is I used WBPP to calibrate the data and register the images in the normal way, and these are just registered right on the stars. And then you need to normalize each color channel, and using the, in this case, the normalized scale gradient script is really the best tool at the moment for doing this job. And it highlights one of the most important aspects of the success of producing an image that looks like this, which is that you need the background sky to be uniform. You need to remove any flat errors and gradients and things like that. And in addition, you also want to take care of residual stars that are not rejected or subtracted or in some other way extracted or removed. And that is one of the big issues with producing cometary images. And I have a solution that I think is powerful. Now, there is never perfect processing when it comes to this because these comets are moving against the sky, the background stars. But I think that there are some ways of really moving the ball forward to get better results. So, where I deviate from the standard method, let me show you what the standard method is first, and then number 3 is where I deviate. The standard method is to use the Comet Align process here, Comet Alignment process here. Comet Alignment does this cool thing where you can align the images on the comet, which I still use, and then you do this rejection, so you can reject all the stars and you get a comet-only image. And then you can also create a star-only image that hopefully rejects the comet by subtracting it from the star image. All of this tool relies on a couple of things. It relies on the ability to use rejection through the number of frames that you have. And if you don't have a lot of frames, you're stuck. And the other thing that it does is it uses subtraction to get rid of the comet, but that requires good linear fits, which means that if the data doesn't fit very well for whatever reason, again, you get kind of stuck. So here is where I have suggested a different route, a different way to go. What I suggest you do is you don't do subtraction and rejection. You do extraction through one of these neural net algorithms using a process like either StarNet++ or what I used in this case is Star Exterminator by Russ Croman. And then you get these two images. You get star images and starless images, which is just comet-only images. And that's the foundation. That's where you begin to work on the data. That's what I think, one of the cool things of being able to use PixInsight in different ways. So the next thing to do is I chose to work on the stars first. So I integrate the star-only images and I create an RGB image of just the extracted stars. Let me show you what I mean. Here is some of the data. If I go open them up, I'm just going to go ahead and open up just some calibrated data. This is the NSG version. The comet's brightest in green, so let's just look at one of these. Here is what the normal data looks like. This is data that has not yet been made uniform by DBE or anything like that. So this is just the NSG data at this point, which is good stuff to work from. And then you go ahead and extract the stars and create starless versions of the image. So you'll find that here I have exactly that. I saved them in 2 different directories here. I have the stars only data in each of the colors. You can see the colors are here, red, green, and blue. So let's look at, I don't know, green, doesn't matter. This is what one of these images looks like. Now there's satellite trails and things, but that'll get rejected just as normal when you integrate these images together. It looks a little funny here just because the auto stretch, it's basing this background where the auto stretch is based on the background where there is no background. So the stars look all weird and blown out. But if we get our, where is my screen stretch thing? Screen transfer function. Let me go grab it. Screen transfer function here. There we go. If we display this in a way that is a bit more normal, like this, now you can see we just have basically extracted stars here. Now with this particular camera, these stars are so small that they look like little dots anyway. But that's a normal star field anyway in green. And then the comet-only data, the extracted data, looks like this. There it is. And that's what it looks like in green. Again, has yet to be DBE'd. which is one of the most important steps here to get that uniform background. So you'll see that I suggested here that after you create those images, I just start working on the stars only. I create a combined red, green, and blue of just the stars, and then make an RGB image out of that. And here's the cool part of what I did. Now let's see if I have those the RGB stars here. So here are the RGB stars, and one of the cool things about getting the colors of the stars correct is that even though this is this weird extracted thing, you can still use PCC, photometric color calibration, to calibrate this image because there are actually stars. It works out just fine. It matches up with the catalog and you get the coefficients that are necessary. To later, you'll apply those same coefficients to the Comet image as well. So I have a stars only correctly colored star field, and then I of course need to somehow align the Comet images because the Comet images right now are not aligned. If I show you that using blink, there you can see as I blink them, you can see the Comet is not yet aligned, and this is where the Comet alignment tool is very useful because there's a cool method of aligning the Comet based on the timestamps that are associated with each image. You'll notice it's not going in order because these images are currently based on the file name. They're being ordered by their weight. This is when the comet was lowest in the sky. You'll notice that it's one of the smaller numbers rather than when it was higher in the sky. You get the better weight. And that's all coming from the measurement of NSG. So let's close this. And then we can look at the actual, aligned images. Let me show you what the alignment process looks like in Comet alignment, if you haven't seen it before. Comet here. There we go. Now these have all of the images. You would technically do this on each of the red and the green and the blue data. You can align them all here, all at once. And because it looks at the timestamp, it will show you which file is the earliest and which is the latest. And then because the comets move in a linear fashion, it can do the alignment measuring the motion between, knowing how to align, shift the images, how to align the comet. So I'm just going to do this. You basically select in the first image, you just click on the comet, and in the last image, again, you click on the comet, and it does all the cool stuff in between for you. You just output the files, and those would be the comet aligned files. Those comet aligned ones I can show you as well, which is really cool. So you go here to registered, and I'll just go ahead and open them up real quick. So this is all I used comet alignment to do. And you can see the comet is aligned, but we get all kinds of shifting things. You'll notice that in the course of creating these starless images, there are these little ghostly things here from stars. That doesn't look like a big deal right now, but wait until you do DBE to this thing. When you remove the major gradient and flat field error, then you see a lot more. So let me go ahead and show you, kind of going back in time here. I take those comet aligned images and I create a combined red, a combined green, and a combined blue that I, of course, put together to create the RGB image of the comet alone. And that's what this is here. But if I go forward in time, you can see what happens when I apply DBE to the image. And now when you've removed that background of non-uniformity, if you will, all that excess stuff, now you can see what what's left over of these kind of star residuals. Now let me just say that this is much less than you would generally get when you use comet alignment, because these residuals are based on a completely different method of the extraction of stars, right? And generally you'll have fewer of these things and they'll be fainter than they will appear potentially in the comet alignment version, which again relies on rejection and or subtraction to do its job. So let's visit again this workflow. You can see that I color calibrated the stars only image. Then I used, as I just mentioned, the Comet alignment process to register the comet in each channel. I integrate those images together to create that RGB. Apply DBE, as I said. Color calibrate the starless that image. You need to color calibrate it because there isn't any information in there. There's no stars to compare to. But you already know the answer from up above when you did the stars only image. You know what the coefficients are, so you just multiply the image by the appropriate coefficients and then you're color calibrated. That's done. And here at step 10 is the part that I think is also critical, and it's the thing that is the kind of the atom block special thing, that secret sauce, I guess I should call it, that helps in making these images look even better. There is a clever way, I think, to create what I would call a star residual mask. So the residuals of stars. And this applies to both the comet alignment process, or if you do this other method of extracting stars with star exterminator. Either way, you're still going to be left with some stuff. And it's easy to capture it. Here's what you do. You just need to create the image of a comet-aligned image with the stars, and you just average everything together. So that's what I was showing here in the comet-aligned process before I closed it here. Let me just show that to you again. Comet alignment. You see, I have all the colors here, and the stars are in these images. So I align the comet with the stars, and then I use image integration just to average everything together. So what I'm going to end up with is a comet image that's, for every frame that'll all be aligned, but then all the stars will be little dots in the image. So let me show you what that image looks like. Here it is. Here's what that image looks like. You can see that I've just averaged all the images. You have the comet here, and then you have all of the stars. So this is the motion of the comet in 5 minutes, because each one of these dots, regardless of the color, these are all the colors, were separated in time by 5 minutes. So that's how much the comet moved in that time to get these little dots. But each of these dots is a smear that you'll see as a residual if they're not completely either rejected or extracted or whatever it is, whatever method you have. So the trick is you average these frames together to create this image, and then you can subtract the comet out, actually. So you subtract the comet away, and then you're left with just the brightest of the trails, like this image. Because if you look at just that comet image that we had a moment ago, the trails they're not that bad. You're only seeing the very brightest things. You're not seeing all of them. Here it is. So you're not seeing all of the stars, and that's because the extraction that's done by a star exterminator is so good that very few things are actually left behind. Keep in mind that eventually, we're going to display the image like this. So the star residuals are there, and we need to capture them. And you can always go around with Photoshop or whatever and clean up the image, but I'm trying to demonstrate what if you had 1,000 of them? I'm trying to demonstrate how you can do this in a systematic way in PixInsight. And so you capture that information here, and then moving forward, I dilate it, I blur it, and then that's just the permanent version of it. And then you can subtract the comet from the image. Again, you can just subtract that comet from it, and you're left with a tool that you can use to apply to this image and remove those residuals. So once I removed the residuals, I applied this mask here to this image here. How you remove the residuals, you can use MLT, or you can try to match the background by using the median in pixel math. And then you end up with an image that looks like this one here. I've also performed here, I've done a little bit of the noise reduction. And I've made the background dark, though it's not totally dark. But I've made it dark. So there are no longer do you see any of the star residuals. And then the final step is to take this image with your final stars only image, the RGB stars only image, and combine them with pixel math. And I think I still have, I have a mess on here, but I think I still have that pixel math here somewhere. Here it is. So if I apply that, you get the answer, which looks like this. So that, that is the result that I was going for. And this doesn't have yet really any, I didn't do any other processing. I mean, you can make the image brighter and adjust the color saturation and all that kind of stuff. But just as a functional process, that I think is a very nice method to approach cometary imaging in PixInsight. So let me just do a final scan of my the steps that I said. Yes, you create that mask, you apply the mask, as I said, and then you permanently, oh, I didn't say it, but you permanently stretch, the stars only image with the image that you created of the comet. And so let me go back here. These two images that I'm showing, all I'm saying here is that this is actually a permanently stretched image. You'll see that it's no longer a linear image. So I kept everything linear until that last point where I'm ready to combine now two permanently stretched images together to create this final version. And basically I'm just using lighten here. That's what Max does in Pixel Math. I hope you enjoyed this kind of overview. And for more detail, I have this in all of its detail, how to do this at Atom Block Studios. Of course, I try to do clever ways or creative ways of putting together all kinds of different data in my tutorials. This actually exists in the Horizons library of material because it has a number of steps to it, so I think it belongs in that section. Though I always recommend people should start with fundamentals. There's plenty of information there, and then proceed to Horizons, where you get to do more of these more either specific or multi-stepped kinds of image processing. Again, go out, take some cool pictures of the comet. As is said, smash that like button, comment below. Perhaps you've taken some pictures of the comet and you have a similar kind of experience in processing. Let me know in the comments what you thought about this kind of approach to processing cometary data. And clear skies. Have fun.